Hey everyone, and welcome back. Today, we're diving into Chapter 5 of our journey into AI, a topic that's been gaining a lot of buzz lately: neural networks. For a long time, things like natural language processing and image recognition were major weaknesses for AI. But with the rise of neural networks and deep learning, we've seen some incredible breakthroughs. This chapter is broken down into 3 sections. Section 1. The fundamentals of neural networks. Section 2. How to build neural networks. Section 3. Advanced neural network techniques. And as always, you can join the AI Fundamentals course community to discuss this chapter and ask any questions you have. The story of neural networks. Our story begins with a fascinating question. How does the human mind work? Our quest to understand our own brains, which are the result of incredibly complex neural processes, is one of the big reasons why neural networks have captured so much attention. The other reason is the huge leap in machine learning we've seen recently, thanks to combining massive amounts of data with powerful deep learning techniques. So, what exactly is a neural network? To really get it, we need to start small, with the individual units that make it up. A neural network can be a biological one, like the one in your head, or an artificial one built with a computer. Key concepts. Let's start with a few key terms. Deep learning. Deep learning is a specific type of machine learning where we link together multiple layers of simple processing units into a network. Input data passes through each layer one by one. This structure was inspired by how the human brain processes visual information from the eyes. This depth allows the network to learn more complex patterns without needing an overwhelming amount of data. Neurons, cell bodies, and signals. Both biological and artificial neural networks are made up of a huge number of simple units, or neurons, that receive and transmit signals to each other. A neuron is an incredibly simple information processor, made up of a cell body and links that connect it to other neurons. Most of the time, a neuron just sits there, quietly monitoring the signals coming in through its links. In biological terms, the links that carry signals into a neuron are called dendrites. The link that carries a signal out is called an axon, which may connect to one or more dendrites at junctions called synapses. On its own, a single neuron seems pretty useless. But when you connect them all together, the resulting system can become incredibly complex. We don't have to look far for proof. Just look at the human brain. The system's behavior is determined by how the neurons are connected and how each one responds to incoming signals. This ability to adapt is the starting point for things like memory and learning. The big picture. Why build artificial neural networks? The primary reason we build artificial models of the brain is to help us with neuroscience, the study of the brain and nervous system. It's an exciting idea. If we can map the human brain in enough detail, we might unlock the secrets of consciousness and perception. A quick note on brain modeling. You may have heard of initiatives like the Brain Initiative, started by US researchers to develop technologies for imaging and modeling the brain. Other projects, like the Human Brain Project in 2012, have had even bigger ambitions, promising that we'd soon be able to unlock the secrets of the mind. While some progress has been made, these ambitious promises haven't fully panned out, raising questions about the massive investments made. Even so, while a complete understanding of consciousness might be a long way off, we've made huge strides in neuroscience. By better understanding the brain's structure and function, we can do some amazing things. For example, we can identify when a brain is malfunctioning and help it restore normal operations, which could lead to new treatments for people with neurological disorders, like epilepsy, Alzheimer's, or issues from developmental problems or injuries. A glimpse into the future. Brain-computer interfaces. One exciting area of research is brain-computer interfaces, which allow you to interact with a computer using just your brain activity. Current interfaces are still pretty basic. They can be used to create a very rough visualization of what a person is seeing, or to control robotic arms. One day, we might have a true mind-reading machine that allows for precise instructions. But for now, that's still science fiction. The idea of feeding information into the brain with tiny electrical pulses is also being explored. While this is used for some therapeutic purposes today, feeding in detailed information like specific words, thoughts, or memories is still firmly in the realm of science fiction. The real reason for artificial neural networks. Okay, enough daydreaming. Let's get back to our course. The other, and arguably more important, reason for building artificial neural networks isn't to understand biological systems, but to be inspired by them to develop better AI. It just makes sense, right? The brain is a master information processing system, capable of producing a huge range of intelligent behaviors, and sometimes some less than intelligent ones. So, it's a logical place to look for inspiration when we're trying to build AI systems. Since the 1960s, neural networks have been a cornerstone of AI. They've gone through periods of hype and periods of stagnation, which we'll get to in a later chapter. But today, they're back in the spotlight, with deep learning driving huge advances in areas like natural language processing and image recognition, fields that were once AI's weak spots. What makes neural networks different? The neural network approach to AI is different from what's called the logicist approach. The logicist idea was that to achieve human-like intelligence, we need to mimic high-level thought processes, specifically manipulating symbols that represent concepts using logical rules. The neural network principle is that if we can just mimic the low-level, sub-symbolic data processing at the level of neurons and networks, intelligence will emerge naturally. This is similar to how we build airplanes. We don't build them to flap their wings or make them out of bone, muscle, and feathers. Similarly, in artificial neural networks, the inner workings of biological neurons are often simplified. The goal is to build powerful AI systems, not to perfectly copy biology. Neural networks have a couple of key differences from traditional computers. Feature 1. Parallel processing. In a traditional computer, a single central processing unit, CPU, does all the work, focusing on one task at a time. The CPU pulls data from memory, processes it, and stores the result back in memory. Data storage and data processing are two separate components. In a neural network, the system is made up of a huge number of neurons, and each neuron can process information on its own. Instead of one CPU handling one thing at a time, the neurons process a massive amount of information all at once. Feature 2. Integrated memory and processing. In neural networks, data storage, memory, isn't separate from data processing. Neurons both store and process information at the same time. Short-term data can be stored in the neurons themselves, while long-term data is stored in the connections between them, called weights, which we'll discuss later. These two differences mean that neural networks are better suited for different tasks than traditional computers. While you can simulate a neural network on a traditional computer, they really shine when you use specialized hardware that can process many things at once, a concept called parallel processing. This is why GPUs, graphics processing units, have become so important and cost-effective for large-scale deep learning. How to build a neural network? As we said before, neurons are very simple processors. If you remember our discussion of linear and logistic regression from Chapter 4, you'll see that the basic technical details of neural networks start from a very similar principle. The basic artificial neuron model uses a set of adaptive parameters called weights, just like in linear and logistic regression. These weights are used as multiplication factors for the neuron's inputs, and the results are added together. The sum of the weighted inputs is called the linear combination. You can think of it like a shopping bill. You multiply the quantity of each item by its price, then add them all up for the total. So, if a neuron has 6 inputs, we need 6 weights. The weights are like the prices, and we also usually use an intercept term, just like we did in linear regression. This is like a fixed credit card fee. We can calculate the linear combination like this. Linear combination equals intercept plus open parenthesis weight 1 times. Input 1 close parenthesis plus open parenthesis weight 2 times input 2 close parenthesis plus open parenthesis weight 3 times input 3 close parenthesis plus weight 6 times input 6. The weights are learned from data using the same principles we discussed before. But before we get to that, the neuron performs one more important step. Activation and outputs. Once the linear combination is calculated, the neuron performs another operation. It takes the linear combination and feeds it into something called an activation function. Common examples include the identity function. Does nothing and just outputs the linear combination as is. The step function. If the value of the linear combination is greater than 0, the neuron fires a pulse on. Otherwise, it does nothing off. The sigmoid function, a softer version of the step function. If you use the identity function, the neuron is exactly the same as a linear regression model. That's why the identity function is rarely used in neural networks. It doesn't do anything new or interesting. The output of the neuron, determined by the linear combination and the activation function, can then be used for predictions or decisions. For example, in a self-driving car, the inputs might be the pixels of an image, and the output could activate the brake system if a stop sign is detected. Learning happens when the weights are adjusted, so that the network produces the correct outputs. Because many neural networks are so big, the largest have hundreds of billions of weights, optimizing all of them is a massive task that requires a huge amount of computing power. Perceptrons, the mother of artificial neural networks. A perceptron is a fancy name for a simple neuron model that uses the step activation function. It was one of the first formal models of neural computing, and you could say it's the mother of artificial neural networks. Introduced in 1957 by psychologist Frank Rosenblatt, the perceptron was designed for simple binary classification tasks. It was a simple algorithm for learning the weights from data. We won't go into the details here, but the basic principle was to feed the network training data, and any classification errors would cause the weights to be adjusted. Hype and reality in AI. The perceptron got a lot of attention, thanks in part to some very optimistic claims from its inventor. One famous example of this hype was an article in the New York Times in 1958, which claimed a new electronic computer would one day be capable of walking, talking, seeing, reproducing itself, and being conscious of its existence. Sound familiar? This kind of over-optimism isn't new. It was also seen with logic-based expert systems, and, as a result, led to 2 AI winters. Periods in the 60s and 80s where funding for AI research dried up. Putting neurons together. Networks. A single neuron is far too simple to make reliable decisions or predictions for most real-world applications. To unlock the full potential of neural networks, we use the output of one neuron as the input for others, and so on. The final output of the entire network comes from a specific subset of neurons called the output layer. We'll come back to this as we learn how to adjust a network's parameters based on the data it receives. Layers. The structure of a network often consists of multiple layers. The input layer has neurons that receive their inputs directly from the data. For a picture, the input layer would use the pixel values of the image. A network also usually has hidden layers that take the outputs from other neurons as their inputs, and their outputs then become the inputs for the next layer. Finally, the output layer produces the network's overall output. A well-known example of a multi-layer network is the multi-layer perceptron. Rosenblatt's perceptron algorithm could learn the weights for a single perceptron, but the learning problem for a multi-layer perceptron was much more complex. It took a while to find an effective solution. The eventual discovery of the backpropagation algorithm in the late 1980s led to a huge resurgence in neural networks, and it's still used in many modern deep learning solutions. Advanced neural network techniques. In the previous section, we covered the core principles behind most neural network techniques. Multi-layer networks, non-linear activation functions, and learning rules like backpropagation. These principles form a solid foundation for almost all modern neural network applications. However, some innovative and continuous developments on these foundations have led to the huge progress we've seen in deep learning and to some truly amazing achievements. Convolutional neural networks. One field where deep learning has been incredibly successful is image processing. The simple classification model we just discussed is very limited. As we saw, it couldn't even correctly classify all the smiling faces. In principle, adding more layers to the network and using backpropagation to learn the weights could solve this. But in practice, another problem emerges. The number of weights becomes so large that the amount of training data needed to get good accuracy becomes unmanageable. A clever solution to the problem of too many weights is a special kind of neural network, or rather, a special kind of layer that can be included in a deep neural network, called a convolutional layer. Networks that include convolutional layers are called convolutional neural networks, CNNs. The key feature of a CNN is its ability to detect image features, like bright or dark spots, boundaries between different regions, patterns, and so on. This is used to build more complex models that can recognize things like a cat's ears, a dog's snout, a person's eye, or the octagonal shape of a stop sign. Training a neural network to detect these features is tricky because they can appear in different positions, orientations, and sizes in the image. If an object moves or the camera angle changes, the pixel values change drastically, even if the object looks the same to us. For a network to learn to detect a stop sign under all these different conditions, it would require a massive amount of training data. A CNN, however, can recognize an object anywhere in the image, regardless of where it appeared in the training images. CNNs use a clever trick to reduce the amount of training data needed to detect objects. They use a single set of weights for many neurons, allowing them to detect the same feature at different locations in the input image. For example, we might have a group of neurons that are all activated by a pointy cat ear. When a photo of a cat is input, two neurons would be activated, one for the left ear and one for the right. We can also adjust the size of the area a neuron sees, so different neurons will respond to different sizes of the same feature, allowing us to detect small cat ears, even if our training data only included pictures of big cats. Convolutional neurons are typically put in the lower layers of the network, which process the raw, pixel-level data. The more basic perceptron-like neurons are in the upper layers, which process the outputs of the lower layers. The lower layers can often be trained using unsupervised learning without a specific prediction task in mind. Their weights are adjusted to detect features that appear frequently in the input data. With pictures of animals, the typical features would be ears and snouts. With pictures of buildings, they would be architectural components like walls, roofs, and windows. If you use a mix of different objects and scenes as input data, the features learned by the lower layers will be fairly general. This means pre-trained convolutional layers can be reused for many different image processing tasks. Do neural networks dream of electric sheep? Generative adversarial networks. If a neural network is trained on data, we can use it for predictions. But what if we want it to create something new? We can get some amazing results if we study the pre-trained lower layers and how they see the features they've learned. We can do this by generating images that activate a certain group of neurons in the lower layers. By showing these generated images back to those layers, we can see what the neural network imagines a particular feature looks like, or what it sees a picture containing a specific set of features to be. That's why some people like to talk about neural networks dreaming or imagining images. Check out Google's Deep Dream system. A word of caution on metaphors. Just a quick reminder about using metaphors like, the neural network is dreaming. A neural network isn't actually dreaming in the true sense of the word, nor does it understand the concept of a cat in the same way a human does. It's simply been trained to recognize things and can generate images that resemble the data it was trained on. Remember what we talked about with weasel words in Chapter 1? To generate realistic-looking pictures of cats, human faces, or other things, instead of just images that look like the training data, a former Google Brain researcher named Ian Goodfellow came up with a creative idea. He proposed pairing two neural networks together in a competitive way. One network is trained to generate images that look like the training data and is called the generative network. The other network's job is to separate the images generated by the first network from real images from the training data. This is the adversarial network. Together, they form a generative adversarial network, or GAN. The system trains both models together. At the beginning of the training, it's easy for the adversarial model to tell the difference between real images and the clunky attempts from the generative model. As the generative model gradually gets better, the adversarial model also gets better, and the cycle continues until the generated images are indistinguishable from the real ones. The generative network isn't just reproducing the images it was trained on. It's trained to be able to generate new, realistic images as well. Could you tell that these weren't real people? The rise of large language models. As we just discussed, convolutional neural networks work by reducing the number of trainable weights in a neural network so that the amount of training data needed doesn't grow uncontrollably as we build bigger and bigger networks. In addition to CNNs, another innovative mechanism that currently powers many modern deep learning models is called attention. The attention mechanism was originally developed for machine translation. It allows a model to selectively focus on specific words in the input text while generating a particular word in the translated text. This makes the learning task much easier since the model doesn't need to focus on all the inputs at once. It was quickly discovered that the benefits of attention mechanisms went far beyond machine translation. In 2017, a team at Google published the famous paper Attention is All You Need, which introduced a deep neural network architecture called the transformer. Unless you've been completely cut off from the news, you've almost certainly heard of transformers, the neural network models, not the toy series.